Hello, this is John Miares, and as we head into Chapter 7 of the textbook, we are going to be looking at some of the hardest material in the course to grasp. In Chapters 5 and 6, we spent a lot of time looking at trigonometric functions, first from a geometric perspective as ratios of sides in triangles. Then we redefined what an angle was so we could apply these trigonometric functions to angles where the angle could be represented as a real number, either in radians or in degrees. Then switched our perspective to look at things analytically, focusing on how they worked as functions of real numbers, including their domains and ranges, their graphs, their basic shapes, their properties, and their inverses. In this lesson, we are going to start looking at the algebraic properties of trigonometric functions and how they can relate to each other. There are a lot of different identities we are going to explore, some of which we've already looked at, and others which will be brand new. We will be looking at how these identities are interrelated and can be used to convert an expression involving trigonometric functions into completely different functions that might be easier to work with once combined. For parts of this, you will be asked to prove that you can convert one expression algebraically into another and justify your steps along the way. Also, because the nature of these proofs does not translate well into web-based assignments, you'll be expected to complete these proofs on paper, then have pictures taken of them or have them scanned and uploaded to a Dropbox in D2L. On that note, let's get started. The first group of identities we're going to look at are the ones in the textbook simply grouped together as fundamental identities. But looking at what each one does, they can be broken down into separate categories. The first group of identities are referred to as the reciprocal identities, and they are called this because they are based on the idea that every trigonometric function we've worked with is the reciprocal of another one. The relationships shown on this screen are not new. We've already worked with the idea that cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of the tangent, and vice versa. There are two other ones that I've alluded to in the past that I put into the category of special reciprocal identities, and those involve having the tangent ratio be the ratio of the sine and cosine, while cotangent, its reciprocal, is the ratio of cosine over sine. Now, if you weren't sure about these, we could explore them a little further. Let's look at some of these pieces separately, and perhaps we can prove these special reciprocal identities are true. For example, we know that the sine of an angle is comparing the opposite over the hypotenuse, the y over the r, and the cosine of an angle compares the adjacent over the hypotenuse, the x over the r. If we now take the sine of theta and divide it by the cosine of theta, it would reduce to y over r divided by x over r. When you divide a fraction by a fraction, the bottom fraction is going to flip and multiply, and you're going to be able to cancel out the r's, leaving you with just y over x, opposite over adjacent, which by definition is the tangent of theta. The next group we can look at are called the negative angle identities. Although we may not have formally looked at them like this, we have explored the ideas presented with these identities when we were looking at the graphs of the 6 trigonometric functions and exploring their inherent symmetry. Cosine and secant are both even functions, symmetric to the y-axis. So the cosine of the negative angle is going to equal the cosine of the positive angle. The other 4 functions, sine, tangent, cotangent, and cosecant, are odd functions, symmetric to the origin, meaning that when you take the sine of a negative angle, you're going to get the negative sign of what that positive angle would have been. Same with tangent, same with cosecant, same with cotangent. The next group of identities are collectively referred to as the Pythagorean identities. When I look at them, they say that the cosine squared of theta plus the sine squared of theta equals 1. 1 plus the tangent squared of theta equals the secant squared of theta, and 1 plus the cotangent squared of theta equals the cosecant squared of theta. The notation with this exponent next to the trig function is intended to make clear what it is that we're going to be squaring, that I'm squaring the cosine of the angle and not the angle itself. Or here I'm squaring the sine of theta and not angle theta. Another way we can look at this is to use parentheses in the expression, like what you're seeing here, where you're taking clearly here the square of the cosine of theta and the square of the sine of theta, and that sum will always equal 1, or 1 plus the tangent of theta all squared plus the secant of theta all squared, or be equal there. The gods of mathematics introduced this notation here with the squaring in front of the cosine or the sine like this so that we wouldn't have to use parentheses every time we were working with powers of trigonometric functions. So hopefully there will not be any ambiguity as to what it is we are squaring. The proofs of these identities have their foundation in the Pythagorean theorem, x squared plus y squared equals r squared. Let's say I want to prove the first identity, cosine squared of theta plus sine squared of theta equals 1. We're going to start by writing out the equation from the Pythagorean theorem as x squared plus y squared equals r squared. From here, let's take both sides of the equation and divide it by r squared. When we do that, we're going to get x squared over r squared plus y squared over r squared equals r squared over r squared. Now let's regroup what it is we have here. I could rewrite this now as x over r quantity squared plus y over r quantity squared equals r over r quantity squared. Knowing what the definitions of those ratios represent with respect to the trigonometric functions, we can substitute that for x over r, calling it cosine of theta, y over r is the sine of theta, and r over r is just 1. Cleaning up this notation, we will have the cosine of theta squared, or cosine squared theta, plus sine squared theta equal to 1. Let's briefly look at the second Pythagorean identity. 1 plus the tangent squared of theta equals the secant squared of theta. We're going to start with the Pythagorean theorem again, where x squared plus y squared equals r squared. But this time, we're going to divide both sides of the equation by x squared. Doing that will give us x squared over x squared plus y squared over x squared equals r squared over x squared. Next, we'll regroup like we did before to get x over x quantity squared plus y over x quantity squared equals r over x quantity squared. Substituting in their definitions, this becomes 1 squared plus tangent of theta squared equals secant of theta squared, which when we simplify and rewrite using the alternate notation will give us 1 plus tangent squared theta equals secant squared theta. Now, I'm not going to prove the third identity here, as I believe that is left as a homework problem. But the general idea is to do the same process as I did above, but divide both sides of the equation by y squared. So you have x squared over y squared, which will become the cotangent squared, y squared over y squared becomes 1, and r squared over y squared becomes the cosecant squared. I will say that knowing how to prove these isn't going to be as critical as knowing how to use them on the homework and the proofs. So these Pythagorean identities, especially the reciprocal identities, are going to need to be memorized, as you will be using them quite a bit both before the end of this course and in your future courses like calculus. Let's look at some examples that might come up in the homework and the problem challenges where you are applying these identities. Suppose you're told the cosine of angle theta is -7/25 and the terminal side of angle theta lies in quadrant 2. Use the Pythagorean identities to determine the value of the sine of theta. The Pythagorean identity that ties together sine and cosine is the first one that says cosine squared theta plus sine squared theta equals 1. Knowing that the cosine of theta is given as -7/25, we can substitute that into the equation like so. From here, we'll square out the fraction on the left to get 49/625 plus sine squared of theta equals 1. I'll turn the 1 into 625/625, so when I move the 49/625 over to the other side, we'll be able to use the common denominators to simplify that into 576/625. Finally, we'll take the square root of both sides, which will make the sine of theta equal to plus or minus 24/25. The question now becomes what to do with that plus or minus sign. Since we're told that angle theta lies in quadrant 2, and the sine of any angle in quadrant 2 is positive, then our final answer for the sine of theta will be positive 24/25. Let's try a similar example, and perhaps this is a good one to try on your own. Suppose that you're told that the tangent of the angle theta equals -4 and the cosecant of theta is positive. Use the Pythagorean and reciprocal identities to evaluate the secant of theta and the cosine of theta. Why don't you pause the video and see what you can do on your own? The Pythagorean identity that involves tangent is the second one that says 1 plus the tangent squared of theta equals the secant squared of theta. Given that the tangent of theta is -4, we can substitute that into our equation and square out the 4 to get 1 plus 16 equals the secant squared of theta, or secant squared of theta equals 17. Taking the square root will give us the secant of theta equals plus or minus the square root of 17. Next, we have to decide whether to use the plus or the minus in our final answer. To do this, let's look more closely at the information given in this problem. If the cosecant of theta is greater than 0 and the tangent of theta is less than 0, then angle theta must lie in quadrant 2, because that is the one quadrant where both cosecant is positive and tangent is negative. Since what I'm looking at is the secant, we need to remember that in quadrant 2, that the secant and the cosine are both negative. So the secant of angle theta will be the negative square root of 17. As for the cosine, that's just going to be the reciprocal of the secant. So that will come out to negative 1 over the square root of 17, or when we rationalize the denominator, it will become negative square root of 17 over 17. This one is a little different. Write an algebraic expression for the secant of theta using only the sine function and assuming that angle theta lies in quadrant 2. So this one might have people scratching their heads because the one identity we know that will relate the secant to anything says that the secant is the reciprocal of the cosine. And we don't have anything that will directly connect the secant back to the sine. However, we do have a Pythagorean identity that connects cosine to sine that says cosine squared plus sine squared equals 1. Now, perhaps if we rearrange this and put the two identities together, we might be able to get somewhere with this. So looking at this Pythagorean equation, cosine squared theta plus sine squared theta equals 1, I can rewrite the equation as cosine squared of theta equals 1 minus the sine squared of theta. Then I can take the square root of both sides to get the cosine of theta equals plus or minus the square root of 1 minus the sine squared of theta. Since we're in quadrant 2, we know that the cosine and the secant are both going to come out negative. So that means we're going to want to use the negative square root here. Now, let's substitute this expression in for cosine into our reciprocal identity. If the secant of theta equals 1 over the cosine of theta, and the cosine of theta can be rewritten in this problem as the negative square root of 1 minus sine squared theta, then I can substitute that into the denominator and pull out the negative sign to get my final answer here, that the secant of theta equals negative 1 over the square root of the quantity 1 minus sine squared theta. This one is very similar to the last one, so perhaps you can try this one on your own too. Write an equivalent algebraic expression for the cotangent of theta using only the cosine function and assuming that angle theta lies in quadrant 3. The hint I will give you is to start with the special reciprocal identity, which says that the cotangent of theta will be the cosine of theta over the sine of theta. Go ahead and pause the video for a few minutes so you can try this one on your own. Again, since we only want our final answer to contain cosines, we need to figure out a way to get rid of this sign in the denominator. To do so, we're going to go back to the Pythagorean identity cosine squared theta plus sine squared theta equals 1. This time, we're going to rearrange it to isolate the sine of theta. So we're going to get the sine squared of theta equals 1 minus the cosine squared of theta. And when we take the square root now, that will become the sine of theta equals plus or minus the square root of the quantity 1 minus cosine squared of theta. Now remember, in quadrant 3, sine is always going to be negative. So given the choice between the positive and the negative, we will want to choose the negative answer here. Substituting that in for the sine in the denominator of the fraction, we'll get that the cotangent of theta will equal the cosine of theta divided by the negative square root of 1 minus the cosine squared of theta, which we can clean up if we want by just bringing that negative out front. Now, some of you might be asking, why should this expression be negative if the cotangent in quadrant 3 is already positive? Well, let's take a closer look at this expression. The cosine in quadrant 3 is already negative, and because of this square root sign, this normally would come out positive. So in order to guarantee that the overall ratio will come out positive, I will take this negative cosine and divide it by the negative radical, and that will reduce to a positive result. So if I didn't have this extra negative sign out here, I actually would end up with an answer that was negative, and I need to make sure my final result is going to divide out to something positive because my angle theta lies in quadrant 3, and in quadrant 3, cotangent comes out positive. Here's one that's a little bit different. Perform the indicated substitution, then use the trig identities to simplify the expression. We're given x equals the tangent of theta, and we want to substitute that into the fraction x over the square root of 1 plus x squared. Why don't you pause the video and give this one a try on your own as well? Well, the fraction x over the square root of 1 plus x squared, after we substitute in the tangent of theta for x, is going to become the tangent of theta over the square root of 1 plus the tangent squared of theta. If we look under the square root sign down here, what you will see is that this is going to follow that second Pythagorean identity. And so I can reduce what is under the radical sign to secant squared theta. The square root of secant squared is going to just be secant. So now I have the tangent of theta over the secant of theta. Now the question becomes, could we simplify this any further? If I break down each of those terms using the reciprocal identities, I can turn the tangent into sine over cosine and the secant into 1 over cosine. Dividing two fractions means I want to multiply by the reciprocal of the one on the bottom. We're going to flip and multiply, and then we're going to reduce this expression by canceling out the cosines, which will leave you with a final answer of just sine of theta. Because of the periodic nature of these trigonometric functions, there are sometimes ways that they can be algebraically manipulated to look like other functions with trigonometric functions based on their properties. The trick sometimes is in recognizing how those properties interrelate to one another and recognizing that most of the standard rules of algebra do not always apply. Where this is going to come in handy is as we move along, if we can understand how these trigonometric functions can relate to each other, and we can use that information to simplify what may look like a very complex expression, then we can save ourselves a lot of time and effort with the downstream processes. For example, looking back at what we were just doing on the previous slide, if I was to ask you to graph the function f of theta equals the tangent of theta divided by the square root of 1 plus the tangent squared of theta, and perhaps ask you about its domain, its range, or any other information, but you were able to manipulate this function to reduce this to just plain old sine of theta, questions like that would be much easier to deal with since we already know what the graph of a sine function looks like. In some of the problems in section 6.1, you will be asked to perform algebraic operations on various expressions with the goal of simplifying them as far as possible. Although the answers to these may be in the back of the book, what you may be graded on is the process to get the final answer itself rather than on just the final answer. Let's try a few examples. These all involve working with trigonometric functions and the distributive property. You're to perform the indicated operation, then determine if one or more identities can be used to further simplify the expression. Our first example is here, where I'm taking the tangent of x and multiplying that by the cosine of x minus the cosecant of x. Now, don't freak out about the idea that we're not using angle theta in this example. Part of our work in chapters 5 and 6 was to get us to think about these trigonometric functions as functions of numbers and not just properties that are tied to angles in triangles. So for all intents and purposes, we can call these functions of x. The idea here is that we want to distribute the tangent through the parentheses, and when we do that, you'll get tangent of x times cosine of x minus tangent of x times cosecant of x. Now the question becomes, is there anything we can do to further simplify the results of this? Well, what if we turned everything in the expression into their equivalents using sines and cosines with the reciprocal identities? The tangent turns into sine over cosine, and the cosecant turns into 1 over sine. So our expression now looks like this. Now, this doesn't look much better yet until you realize that there are some things that can cancel within each term. In the first term, the cosines will cancel, and in the second term, the sines cancel, leaving you with sine x minus 1 over cosine x. If we wanted to take this one step further, we could look at the reciprocal identities one last time to get a final answer of sine x minus secant x. Let's look at another example. Let's say I'm taking 1 minus sine of t times 1 plus sine of t. The notation suggests that I want to multiply out these expressions using the FOIL method. First, outside, inside, last, which will get me this as a result. 1 plus sine t minus sine t minus sine squared t. Of course, this follows the difference of two squares pattern, so we can combine the two middle terms so they will cancel out and give us 1 minus sine squared of t. Now from here you might ask, is there anything else we can do with this? Well, whenever you see a trig function being squared like this one, it's possible that they can be further simplified by using one of the Pythagorean identities. So we need to think about how that might apply here. We have one identity which says that the cosine squared of theta plus the sine squared of theta equals 1. And we could actually use that in a few possible ways. I can substitute that entire expression in for the 1 right here, or we could rearrange the expression to say cosine squared equals 1 minus sine squared of theta, and have that be what I substitute in above. Or alternatively, we could rearrange this as sine squared equals 1 minus cosine squared and substitute that in for the sine squared up above. No matter which of those three cases you choose, this expression is going to simplify to just plain old cosine squared of t. Let's try a few that involve factoring. In the first one, we have the secant to the fourth power of x minus the tangent to the fourth power of x. We should recognize this as having the potential to follow a difference of squares pattern where a squared minus b squared can be factored as a minus b times a plus b. Except with the fourth power, we need to think of this as something squared squared. Following the pattern, this can break down as secant squared x minus tangent squared x times secant squared x plus tangent squared x. From here, again, what I see are a bunch of squared terms, so perhaps a Pythagorean identity may be of use. The second Pythagorean identity says 1 plus the tangent squared of theta equals the secant squared of theta. So I can substitute that in everywhere I see a secant squared, which is going to give me this expression that only has tangent squared terms in it. Now let's combine the like terms. In the first portion, the tangent squared terms will cancel, while in the second factor, they combine to give 2 tangent squared x, and that can be our final answer. Now, we could have rearranged this all to just have secants in it and to say that the tangent squared of theta equals the secant squared of theta minus 1, then simplify it that way. Where this can get tricky is that it isn't always clear how far we need to go to simplify the results as far as we want. Now let's try this one, which is set up to be a difference of two cubes. You may not remember the factoring pattern for the difference of two cubes off the top of your head, and it is in a reference page in the front of your textbook. But if you don't have a hard copy of the textbook, it could be hard to find. So for this one, I'll just give it to you. If you have the expression a cubed minus b cubed, it will factor as a minus b times the quantity a squared plus ab plus b squared. In this case, we're going to be treating a as the tangent of x and b as 1. So this will then look a minus b is tangent x minus 1. A squared plus ab plus b squared is our tangent squared x plus tangent x plus 1. Next, we can think Pythagorean just like we did in the last example where we substituted in 1 plus tangent squared theta equals secant squared theta, which could also look like tangent squared theta equals secant squared theta minus 1, or secant squared theta minus tangent squared theta equals 1. In the first factor, there are no squared terms, but in the second factor, there is both a tangent squared and a 1. So substituting that in will get this to look like tangent of x minus 1 times the quantity secant squared x plus tangent x. Now let's look at some where you're simplifying fractions. Let's say what I've got here is this expression with two fractions multiplied by each other. In the fraction on the right-hand side, we can factor out the cosine of x as a common factor out of the top, and we can factor the denominator as a difference of two squares. Doing this will give us the cosine of x times the quantity cosine of x plus sine of x. In the denominator, I have the quantity sine of x minus cosine of x times the quantity sine of x plus cosine of x. This is all still being multiplied on the left, of course, by the 3 sine x over cosine squared x. From here, let's try to cancel some like terms. The cosine x in the numerator will cancel with 1 power of cosine in the denominator of the left-hand fraction, and the cosine x plus sine x in the numerator and denominator of the right-hand fraction will cancel each other out. That should leave you with 3 sine x over cosine x times 1 over sine x minus cosine x. The last thing we might do is apply the reciprocal identity to get 3 sine x over cosine x turned into 3 tangent x and combine that back into a single fraction, 3 tangent x over sine x minus cosine x, as my final answer. Here's another one which actually looks simpler, but in some ways can be more frustrating. Here we have 30 times the sine cubed of x times the cosine of x all over 6 times the cosine squared of x times the sine of x. Remembering our work with reducing exponents, the 30 over 6 can reduce to 5 over 1. The sine cubed of x over the sine of x can reduce to sine squared of x in the numerator, and the cosine of x over cosine squared of x will leave a factor of cosine of x in the denominator. Now, this time, instead of thinking Pythagorean, I want to separate out the powers to make it look like 5 times the sine of x times the sine of x over the cosine of x. Where separating the powers becomes handy is that I know that sine of x over cosine of x is equivalent to the tangent of x. So if I regroup the terms, separating them out, I can get 5 times the sine of x over 1 times sine of x over cosine of x. Now we'll apply the reciprocal identities and reduce the second fraction to get a final answer of 5 times the sine of x times the tangent of x. Now, this isn't our only possible answer to this problem. Let's back up to where we had up here 5 times the sine squared of x over the cosine of x. Recognizing the square in here, we could think about how we might apply the Pythagorean theorem. The sine squared of x could be rewritten as 1 minus the cosine squared of x. And from there, we would distribute the 5 to get 5 minus 5 cosine squared of x all over cosine of x. Next, we could divide each term in the top by the cosine of x that's in the denominator, which would give us 5 over the cosine of x minus 5 times the cosine of x. Applying the reciprocal identities, this is going to reduce to 5 times the secant of x minus 5 times the cosine of x. Now, this is where things can somewhat get frustrating with these problems because it isn't always clear how we should break down our final answer. Both of these answers in the red boxes are correct. They are both simplifying results of our original problem up here, 30 times the sine cubed of x times cosine of x over 6 times the cosine squared of x times the sine of x. They are both algebraically equivalent expressions of the same function here. For some of the problems in section 7.1, they don't tell you how far to simplify or what direction you want to go until you look in the back of the book for an answer. For many of the later problems that we will do here, and in what we're calling the proof packet, you are basically going to be told where you're starting and where you're ending so you know what the final answer is going to look like. And the focus will be on just how to get there. This is going to be our segue into trigonometric proofs. In a proof, you're not just going to be given a problem that says use the identities to simplify this expression as far as you can, but rather you'll be given a problem which says essentially simplify one side of this equation to get it to look like the other side of the equation and justify all of your steps along the way. This one here might be a good example of where you're told you want to prove that this expression tangent of x plus cotangent of x all divided by cosecant of x can and will reduce to the plain old secant of x. There are multiple ways that we can do this, and I will look at this problem in particular. But first, I want to talk about the fact that the textbook provides multiple possible strategies to verify that two expressions involving trigonometric identities are going to be algebraically equivalent to each other. But the reality is that not all of the strategies presented are going to be proofs in the mathematical sense of the word. The first strategy they introduce is to graph both sides of the equation and show that the two graphs are going to be identical to each other, except possibly at a finite number of points, which may be the domain restrictions of one side of the equation, but not in the other. While getting two graphs to overlay each other will show that they are algebraically equivalent, that is not going to be the most efficient way of approaching any of these problems, especially if on your homework you're not able to show me your graphs. The second strategy is to attempt to solve the equation by manipulating both sides of the equation using known properties of algebra and trigonometric identities and show that everything will either eventually equal each other or cancel out. Again, this strategy will show that the two sides of the equation will be algebraically equivalent to each other. But that in itself is not a proof from the formal standpoint of what is a proof. In our third strategy, which is what I'm going to advocate for here, you're going to be taking one side of the equation and show that it can be rearranged using the properties of algebra and the other known trigonometric identities to get the expression to look like the other side of the equation, justifying each step of the manipulation along the way. So this is the direction that I want us to focus on. While strategy 1 and 2 may meet our needs in many cases, only strategy number 3 would be considered a formal proof. There are various strategies to consider when manipulating trigonometric functions to prove that one side of the equation equals the other side. First, if the goal is to get one side to look like the other side, start with the more complicated side of the equation so that perhaps it can be simplified into the other side. Also, look at what it is you're trying to prove. If it involves fractions, try using reciprocal identities. If it involves squared trig functions, perhaps a Pythagorean identity will help. If it involves double angles or half angles, which we will be exploring in section 7.3, then perhaps those identities can be helpful. You may also need to try doing some various algebraic manipulations like adding, subtracting, multiplying, dividing, distributing, factoring, combining like terms, completing the square even. You can also try modifying the expression by multiplying by factors of 1 using conjugates, reciprocals, or even Pythagorean identities. Sometimes you might try squaring both sides of an equation to see if you can introduce a Pythagorean identity relationship. But that's not always the best idea because, as a general rule, you want to try to avoid manipulating both sides of the equation when you can. When all else fails, you can turn everything into sines and cosines using the reciprocal identities and the special reciprocal identities to see if you can get some things to cancel. So let's see what we can do here with this one. I want to try to prove that tangent of x plus cotangent of x, all divided by cosecant of x, will reduce to just secant of x. Seeing that this left-hand side is a lot more complicated than the right-hand side, we're going to start on the left to see if we can simplify it to look like the right. Also, knowing that this secant of x here is the reciprocal of the cosine, perhaps we can use the different reciprocal identities to turn everything into sines and cosines, and if we can then get everything to cancel out, leaving us with 1 over cosine of x, then we'll be able to get to our final answer. So starting on the left, we have our expression tangent of x plus cotangent of x, all divided by cosecant of x. Applying the reciprocal identities to turn things into sine and cosine, we will get tangent turning into sine over cosine, cotangent turning into cosine over sine, and cosecant turning into 1 over sine. Next, before we can flip and multiply here, let's see if we can simplify that numerator a little bit by getting a common denominator put in here. The common denominator will be cosine of x times the sine of x. So the first fraction needs to be multiplied by sine of x over sine of x, and the second fraction needs to be multiplied by cosine of x over cosine of x. Doing this will give us sine squared of x plus cosine squared of x all over the common denominator, cosine x times sine of x, and then we're dividing all of that by 1 over sine x. Next, let's do a few things. We see in the top fraction, or rather in the top of the top fraction, we have sine squared x plus cosine squared x, which, applying the first Pythagorean identity, will reduce this to just 1. Then dividing by 1 over the sine of x will be the same as multiplying by sine of x over 1 as we flip and multiply. From here, let's cancel out this sine of x in the top with this sine of x in the bottom, and we're going to be left with 1 over the cosine of x, which, if we then apply the reciprocal identity, gets us to the secant of x, which is what we were looking for as our final answer. So this is going to be the basic structure of our proofs. We want to try to take one side of the equation, and rearrange it to look like the other side of the equation without messing or touching with the right-hand side at all. Along the way, we want to justify all of our steps so it's clear how you are getting from one side and one step to the other, and so anybody looking at the processes can feel convinced that what you've done is mathematically justified. Let's try another one. Although this one looks more complicated, it's actually a lot simpler than the last example and should go much faster. What you should see right away is that there's lots of squared terms on the left-hand side of the equation, which tells me that perhaps the Pythagorean identities are going to be very helpful here. So starting on the left-hand side, let's regroup some of the terms so that we can see the Pythagorean identities at play. Cosine squared plus sine squared can combine when applying the first Pythagorean identity to equal 1, leaving you with cotangent squared x plus 1. Now applying the third Pythagorean identity, 1 plus the cotangent squared of x will become the cosecant squared of x. And that is our final answer. The next few examples are not in the notes packet, but happen to be the first few problems from the proof packet. The proof packet basically takes a bunch of problems from the homework in section 7.1 and separates them out so that instead of you trying to figure out how to do all of these in WebAssign in one night, we're going to spread out the efforts and work on a number of these problems over the next 3 weeks. Here's the first problem. We want to prove that the cosine of x divided by the secant of x and the sine of x is equal to the cosecant of x minus the sine of x. Now, one thing I noted earlier in a proof was that you want to manipulate one side of the equation to get it to look like the other. But the side that you manipulate can be the right-hand side if you want it to be. It is much easier to get rid of a plus sign or a minus sign than it is to introduce one in a problem like this. So here, let's actually start on the right-hand side of the equation this time and see if we can get it to look like the left-hand side. So starting with cosecant of x minus sine of x, let's convert everything into sines and cosines using the reciprocal identities, which will make this 1 over sine x minus sine x. Next, when you have a fraction involved in a subtraction problem, we're going to need to get a common denominator, which will be sine of x. Multiplying the top and the bottom of the right-hand fraction by sine of x over sine of x will give us 1 minus sine squared of x all over sine of x. From there, let's apply the Pythagorean identities in the numerator, which will take the 1 minus sine squared of x and turn it into cosine squared of x. So now we want to separate out the powers of cosine so that I can get the cosine isolated by itself. So now I have cosine of x times cosine of x all divided by sine x. Let's look at what it is I'm trying to prove. If I go back to the very beginning, I've got a cosine of x in the numerator, I've got a sine of x in the denominator. In the expression I have so far, I've got a cosine of x in the numerator, I've got a sine of x in the denominator. The only difference between the original expression here that I want to prove and this where I'm at now is this extra cosine of x here in the numerator compared to a secant of x in the denominator. So what I'm going to apply is the reciprocal identity to one of those factors of cosine in the numerator to bring it downstairs so that it becomes a secant. And there is my final answer. Here's one perhaps that you can try on your own. Let's try to prove that the tangent of y over the cosecant of y will equal 1 over the cosine of y minus 1 over the secant of y. Again, it's going to be easier to get rid of a plus or minus sign than it is to introduce one. So just like on the previous slide, I would recommend we start on the right-hand side this time and see if we can rearrange it to look like the left-hand side. Go ahead and pause this video to see if you can give this one a try on your own. So if we start on the right-hand side, we have 1 over cosine y minus 1 over secant y. Applying the reciprocal identities, we have 1 over cosine y minus cosine y. From here, just like in the last problem, we want to get a common denominator in order to combine the two expressions. And we can do that by multiplying the top and bottom of that fraction by cosine y. That is going to get us 1 minus cosine squared y all over cosine y. Next, we'll use a Pythagorean identity to simplify the numerator of the fraction to just sine squared y. Now, before we go any further, we may need to look at what it is we are trying to prove. We're trying to get this to look like tangent of y over cosecant of y. I know tangent is sine of y over cosine of y, and I know cosecant is 1 over the sine of y. If we separate out the powers of the sine so it looks like sine of y times sine of y over cosine of y, we can regroup the terms to get sine of y over cosine of y times sine of y over 1. Well, the sine of y over the cosine of y on the left is going to become the tangent of y when we apply the reciprocal identities, and the cosecant of y, well, if I have it as the sine of y over 1, and I know cosecant of y is the reciprocal of the sine of y, then I'm just going to apply that reciprocal identity to move this sine of y upstairs to become the cosecant of y downstairs. So we can now have this simplified as just tangent of y over cosecant of y. All right, we've covered everything we needed to do in section 7.1. What I'll say is that in the homework for section 7.1 and in the problem challenges for 7.1, there are not going to be any formal proofs. Most of the problems in section 7.1 that I'm going to assign in WebAssign are going to focus on applying the identities like what we were working on at the beginning of this presentation. The proofs that are in that section are going to be left for you to do in the proof packet, which again, we're going to be spreading out the work over 3 weeks. There's 24 proofs you're eventually going to do here, which means we're going to work on 8 proofs per week for 3 weeks, which I think will be a lot better than having you try to do them all in one night in a single assignment in WebAssign. The proofs are important enough that not only do you want to take your time in doing them out, but I will want to see them written out on paper and perhaps give you some help and some strategies on how to do these problems if you get stumped. I'm really not a fan of the way that these problems are presented in the WebAssign homework, so I want to save us all a lot of aggravation and grief by just avoiding having you to do these in an online assignment if we don't have to. Unfortunately, because of the way this class is now set up as mostly an online class, the only way I can be able to see your work if it's done on paper is if you take a picture of it and scan it. That way, then you can upload the file into a Dropbox, and then I can look at it there and be able to give you some commentary and feedback on ways that you can improve your proof strategies. That being said, here are the problem challenge problems for section 7.1. We're going to be talking about these at an upcoming ORT session, so as always, it is best if you can look at these particular problems ahead of time so you know what questions to ask. As always, if you have any questions or worries about these problems, feel free to contact me via email or you can post your question on the discussion board. Thanks for watching, and we'll see you all soon.